right. How are you guys doing?
Good.
Well, there's some kind of feedback. All right, we'll wait another minute for people to show up. Maybe I should start saying something about the website in the meantime. So there's some updates on the website. First of all, there's, I guess, computer assignments are now available. The first computer assignment, I should say, is now available on the website. So you can take a look. If you click on the link, you can see this. So you basically, this should be a pretty straightforward computer assignment. You just need to code Armijo's rule for a quadratic function in Python, and basically check that you are getting to the right answer, because you can actually solve explicitly what the solution to this quadratic is for the minimum, right? It's just Q inverse X. So that you should be able to use matrix inversion to find the solution and then verify your answer. And then there's also a package that you can use, standard package in Python that you can use on the same problem and verify that you're getting similar results. So that's the computer assignment. It's due between homework 2 and homework 3. So homework 2 will be due on September 22nd, homework 3 on September 29th, and on October or something. So this lab will be, the computer assignment will be due on Monday, September 28th. The way it'll be due is that you need to just upload your code to Python. So let's get back to that. So you upload your, I don't know if I can get a pointer on this thing. So if you read there, it says that you should upload your code on or your Python code on Compass 2G before the due date, which is the 28th of September at 5 p.m. And you have office hours between 5 and 7 p.m. During which you're going to demonstrate, one member from your team will demonstrate to the TA, to one of the TAs, that your code works. Okay, so you'll each team will get, there'll be 16 teams right now, so each team will get about 8 minutes, and then during that 8-minute slot, you should run your script and show that it works to the TA. So the way the teams are done, as I said, I assigned the teams. I created the groups for the computer assignments. For the project, which I'll talk about a little bit later, it'll be only for the people who are taking it for 4 credits. That you can form your own teams. Okay, but the teams are actually in an Excel spreadsheet, which I don't know if I can open. I can view. Oh, there we go. So you probably can't see it very well, but this, I guess, on my iPad, the Excel spreadsheet doesn't show the actual teams, but basically we made sure that each. So, for example, in this case, the first 3 people listed here form a team, and there are 2 graduates and 1 undergraduate student in each team. I don't know. There's something strange here. I'll double check. I'll make sure that the team assignment is correct with the TAs.
I think it's the other sheet.
It's the other sheet. There's another sheet. Okay, so I can't do that on my iPad. So sorry. So you guys can open it. and make sure that it is actually what it's supposed to be. But basically, I try to make sure that I told the TAs to make sure that in each team, that I should say every undergraduate student is in a team with 2 other graduate students, and then the remaining graduate students formed their own teams at the end. So that's how we did it. And there'll be 3 computer assignments. So each one of you in the team will take turns demonstrating the code for the computing assignment. So I just need one of you for each assignment to demonstrate the code, although all 3 of you can be on the Zoom call. But one of you needs to open up your laptop or a computer and share the screen with the TA and show that the code works. Okay, so that's the idea. So any questions about computer assignments?
Yeah, hey, real quick, I missed maybe the beginning of it, but did you say that Python is a requirement? Not necessarily we can choose maybe MATLAB or something else?
No, Python is required for this because we're going to give you, point you to, Python code that you can, packages that you can use to check, to verify your other code. So it should be, it's very similar. So if you're familiar with MATLAB, it should be easy enough for you to pick up Python.
Okay, thanks.
All right, so that's what I have for logistics. Oh, and the other thing was in your submission of homework 1, which I think pretty much everyone who is registered for the course, maybe for one or 2, have submitted their homework successfully on Gradescope, except some of you, and maybe you got a message from the TA if you already, had some trouble creating a readable, really legible scan of your homework. So be careful. You guys should be good at this kind of stuff. But if you're using your cell phone, make sure that your scanned pages actually are fit on 8.5 by 11, and it's not like you take a little photo, a little piece of your page, and then append something else. I mean, people have done that, a few people, and it's basically not very legible. So make sure your PDFs actually look like pages that you can easily print out, and that they're legible before you upload it to Gradescope. Okay. So some of you whose homeworks were not very legible, I think the TAs would have sent you messages already to ask you to re-upload. Okay, so please do that. I know this is all a big pain, but hopefully after some initial teething troubles, we'll move along and we'll be just as good as in person. Okay. Sorry about that. All right, so let's get to today's lecture. Actually, before today's lecture, let's actually do a review what we did in lecture 5 on Tuesday. So we started talking about iterative methods for optimization, for unconstrained optimization. So gradient descent is what we started talking about. First we talked about alternatives for how to maybe follow a path where we decrease the value of the function, and then we argued that the direction in which you have the greatest rate of increase is the negative of the gradient, and so that's called steepest descent. Although there may be issues with convergence. Actually, we'll talk a little bit about that today. And so you may not necessarily want to go in the direction of the negative gradient. You have alternatives. So you go along a direction dk that has a positive projection along the negative gradient. And one way to accomplish that is through a matrix. So the direction dk is minus some matrix capital dk times the gradient. Okay, and if dk is positive definite, then you're guaranteed that you you're in a descent direction. Okay, and then we talked about methods for choosing the step size, and of course the best way to choose the step size would be to choose the step size to give you the maximum decrease in the function. That's the optimal line search method, which is given here. But this may be difficult to implement in practice. Then we talked about Army-Hose rule, which is basically a backtracking algorithm. So you try something out for a step size, and then successively decrease it by a factor beta, which is less than 1. And then there's a stopping criterion that you use to decide when to stop decreasing the step size. Okay. And then we talked about convergence. So if you do guarantee that in every step that you're actually decreasing your function, okay, then you can start seeing what does that value xk converge to. Ideally, you would like to converge to at least a local minimum, right? If it's a convex function, that's good enough because any local minimum is also a global minimum. Okay, and we proved basically that Army-Hose rule will take you to a stationary point of f, not necessarily a local minimum. You might be unlucky, and which is rare, and end up at even a local max. But you could certainly end up at a stationary point that's not a local minimum. It could be a saddle point, for example. But as I said, most of the time, these things will tend to local minima will tend to attract these kinds of algorithms. Okay, so in practice, that's what will happen. All right, so that's Army-Hose rule, the proof. What else did we talk about? I think that's all, right? I don't think yeah, that's it. That was the end of the lecture. So today, we're going to talk about convergence of gradient descent with constant step size. So, but before we start, any questions about the material we have covered so far? All right. Okay. So, in order to talk about gradient descent with constant step size, we have to introduce the notion of Lipschitz continuity, or just Lipschitz functions, okay? Because you need some conditions on the function in order to guarantee that with a fixed step size, you'll still converge, okay? And I'll give you examples that if you didn't meet those conditions, right, then you might end up, even though you're going along a descent direction, right? So I'm talking about, just let's talk about just steepest descent. But if you don't choose your step size according to Army-Hose rule, where you guarantee that you always decrease the function in every iteration, then you may end up actually increasing the function. Not only that, you may end up increasing the function in a way that actually eventually it blows up. Okay, instead of going down to a local minimum, we actually go off to infinity. So we'll see examples of that. So what is a condition that you can impose on a function such that it's somehow contained, and as long as your step size is chosen relative to this number, it actually will result in a convergent algorithm. Okay, so for that, let's introduce this notion of Lipschitz continuity. So we say that a function is Lipschitz continuous if there's a number L, which is positive, such that if I look at the difference between a G at some point X and G at some point Y, and G is a vector, possibly a vector valued function. So you're going from Rn to Rm. Okay, so these G's are sitting in Rm. So rather than taking the absolute value, I'll take the norm difference between these two. And this is less than the norm difference between X and Y. for all xy in Rn. Okay, and this L is called the Lipschitz constant. Okay, so this condition is called Lipschitz continuity, or just Lipschitz condition on G. So G is said to be Lipschitz if this condition holds for some L positive. Why do we say that G is continuous? Why do we call it Lipschitz continuous? Why the term continuous? Anyone? Anyone? Okay. If you think about it, the definition of continuity of a function says that if x is close to y, then gx must be close to gy. And you can actually establish that. In fact, you get uniform continuity over the entire space Rn for this function g just by this Lipschitz condition, right? Because that's exactly what this is saying. If I make x close to y, so if I make x minus y less than some delta, right, I can ensure that gx minus gy is less than L times delta. So I can make that less than any epsilon I want for any x and y, right? So this is so Lipschitz continuity gives you uniform continuity in Rn. Okay, that's why it's also called Lipschitz continuous, not just Lipschitz. All right. So examples of Lipschitz continuous functions or Lipschitz functions. Let's look at just functions on the real line. If you look at functions on the real line, anything that has a bounded derivative is going to be Lipschitz. Why? Say gx equal to x or gx equals sine x. Any function that has a bounded derivative is going to be Lipschitz. Anyone have a quick proof or tell me why that would be true? What result will let me conclude that? Anyone? So bounded derivative, what does that mean? Right? No one? So think about Taylor's theorem. What does Taylor's theorem say? So G is a one-dimensional function on the real line. So the G of x is in Gy. What does Taylor's theorem say? And this is basically the derivative of at some point z times x minus y. Right. So this is the exact version. So where z is some point in between. So if you take gy on this side, and you're left with this, as long as g prime of z is bounded, so with the bounded derivative, you have the Lipschitz condition. Right? Okay. Okay. So that's why things like x and sine x are going to be Lipschitz. But it doesn't have to be differentiable. For example, gx equals absolute value of x is Lipschitz. Actually, it's Lipschitz with Lipschitz constant 1. And the proof for this, and it's actually true for any norm, by the way, and we'll see that in just a minute. But the proof of this follows from the triangle inequality. And basically, if you look at x minus y, plus absolute value of y, x minus y plus y is x. So this has to be greater than equal to x by the triangle inequality. And similarly, the same thing, y minus x, which is the same as x minus y absolute value, plus x. Okay, the y minus x plus y is equal to y, so this is greater than y. Okay, and then you combine these two inequalities and you conclude that the absolute value of absolute value of y minus absolute value of x is less than the absolute value of x minus y. So that's how you get that G is Lipschitz. All right. Okay, so and it's Lipschitz with Lipschitz constant 1. So basically, this implies that absolute value of x minus absolute value of y. Absolute value is less than x minus y. So, and this constant here is 1. So that's why this is Lipschitz with Lipschitz constant 1. And this is actually true more generally. So if I have a function from Rn to R, which is the norm of x, same thing, triangle inequality. Any norm will satisfy the triangle inequality. The same proof is shows that this function is Lipschitz with the Lipschitz constant 1. Okay, any questions? Now let's talk about a function that's not Lipschitz. So let's look at g of x equals norm of x squared. And so this, if we look at the gradient of g, what's that equal to? Anyone? Boy, you guys are so quiet. You can unmute. Too late at night for some of you, huh? All right. What's the gradient of x squared, norm of x squared? Boy, you should have done this in your, yeah? 2x, very good. All right, so, and you can, so this is, again, this is not one dimension, but you can see that this x, the norm of x can blow up, right, and Rn, so you wouldn't expect this function to be Lipschitz. And to prove that it's not Lipschitz, you just have to create a counterexample. And there are many ways to do it, but a simple way to do it is just consider y equal to 2 times x, okay? So then, if g is Lipschitz with some constant constant L, we must have that if I look at the difference between gy, so the absolute value of norm of x squared minus the norm of 2x squared, x minus y squared, like this. This must be, again, g is takes values on the real line, so I just took the absolute value, which is the same as the norm on the left-hand side. On the right-hand side, I must have this is less than the norm of x minus y, which is x minus 2x. Okay, for all x belonging to Rn, but this implies that 3 times norm of x squared is less than or equal to L times norm of x for all x belonging to Rn, but this cannot hold. For example, this won't hold for values of x such that this is bigger than L over 3, right? Clearly. So this can't be Lipschitz. Okay, so this is a contradiction. So so you get that G cannot be Lipschitz. Okay, any questions? All right. So again, you can, I'll give you some more examples to do in the homework to get you familiar with the idea of the Lipschitz function. So now let's move on to what's really important for convergence. It turns out what's important for convergence of algorithms is not the function itself, the function f being Lipschitz, which is why on purpose I chose a different symbol for when in the definition of Lipschitz functions. It's basically, it's the gradient of the function being Lipschitz that's important, okay? So let's say, so we look at g of x being the gradient of the function f. So f takes values on the real line, but the gradient takes values in Rn, right? Okay. So and so now the gradient is a function that goes from Rn to Rn. right? It's a vector valued function. And we say that the gradient of f is Lipschitz if it satisfies this Lipschitz condition, right? So grad fx minus grad fy must be less than or equal to L times norm of x minus y for all xy. Okay, so let's look at functions that are gradient Lipschitz. Whose Lipschitz is gradient? Gradient is Lipschitz, whose gradient is Lipschitz, not the other way around. So we just saw this example of a norm of x squared. This is not a Lipschitz function, but its gradient is Lipschitz, right? The gradient of this function is 2 times x, and this is obviously a Lipschitz with, what's the Lipschitz constant? Anyone? Come on, guys, somebody needs to speak up. No? 2, right? It's obviously 2, because it's basically true with equality for xy. Okay. What about the function x to the 4th, the norm x to the 4th, which in one dimension will just be x to the 4th, but let's look at this. What's the gradient of this function? And this will take a little bit more work, but anyone? So the gradient of x squared was so suppose if I didn't have norm of x to the 4th, if I had x to the 4th, what's the gradient then?
I think we need to consider if x is greater than 0 or smaller than 0.
No, x is a vector here.
Oh, if x, okay.
So what's a derivative? So suppose x is not a vector, x is a scalar. What's the derivative of x to the 4th?
It's 4x to the 3.
4x to the 3, very good. So what do you think the gradient of norm of x to the 4th will be for an n-dimensional vector x? Any guesses?
4x transpose x transpose?
Close, not quite, but very close. So it's actually 4. X transpose would be a column vector, a row vector, so you need a column vector. So you're close. It's actually 4 times norm of x squared times x. And if it's not obvious to you why this is the case, try and prove this at home, okay? Just by taking the derivative with respect to each of the components, the partial with respect to each of the components. You should be able to show this, okay? Starting with the fact that norm of x to the 4th will be basically x1 squared plus x2 squared, so on, xn squared to the whole thing squared, right? So that would be, sorry, the square root of that will be the norm. Yeah, so that's to the power of 2, yeah. And you can use that to show that this is 4 times norm of x squared times x, by taking partials with respect to each of the xi's. Okay, so it kind of looks, and it'll boil down to 4 times x cubed if x is a scalar. But you guys need to be comfortable with taking gradients of simple things like this, okay? And then it should become obvious to you eventually. All right, so now let's test to see if this gradient is Lipschitz. For that, again, you can guess that this is not going to be Lipschitz because it's got, if you take, again, I will actually prove a condition about a sufficient condition, sufficient condition for checking whether a gradient is Lipschitz in just a minute, but you can guess that maybe this is not going to be Lipschitz, okay? And again, one way to think about that is to look at the scalar case, in which case you get 4 times x cubed. If you take the derivative of that, that is going to be unbounded, and that gives you a hint that you're not going to be Lipschitz. Okay, so to verify that it's not Lipschitz, you just need to come up with a counterexample. And let's, in this case, this is an odd function. I'll make y equals minus x to construct my counterexample. And the way this will work is that if I look at so y is minus x, so if I look at the gradient minus the gradient at y, will just be plus for y is minus x. So you get that. So this must be less than, if it was gradient, if it was Lipschitz, this should be less than x minus x is x minus y will be x minus minus x will be 2x here for all x belonging to Rn. This must hold. And this implies that 8 times x norm of x squared times norm of x, so it's actually norm of x cubed, is less than L times 2L times norm of x. Okay, this is for all x belonging to Rn. And clearly, this is not possible if what condition holds? If the norm of x squared is bigger than L over 4. Right, this cannot happen. So x to the 4th does not have a Lipschitz gradient. And if you think about it, if you take norm of x to 2 plus any power, 2 plus some alpha where alpha is positive, you're going to have trouble meeting the Lipschitz condition. So it's not going to be gradient Lipschitz. Okay. So a special case of that is this norm of x to the 4th. Now we'll prove a kind of a general result. So f is twice continuously differentiable with the Hessian. So we saw that in the case of a one-dimensional function on the real line, that we had that the derivative being bounded was sufficient to establish Lipschitz continuity. So here something similar should hold for the gradient to be Lipschitz. So for the gradient to be Lipschitz, you need to look at the next derivative, which will be the Hessian. So a condition on the Hessian, you would expect that maybe will give you Lipschitz gradients. And in fact, that's true. So if the Hessian of the function is lower bounded by minus mi and upper bounded by some mi, then the gradient is Lipschitz with Lipschitz constant m. Okay. Now I have to explain this notation a little bit. What do we mean when we say that a matrix is bigger than some other matrix? Now this is the inequality with little curves on it. So what this really means when we say this, when we write this, this says that a minus b is positive semi-definite. A less than b means that a minus b is negative semi-definite. Okay, so that's the notation for it. So what this says is that if the Hessian plus mi, I is the identity matrix, is positive semi-definite, and the Hessian minus mi is negative semi-definite, then the gradient is Lipschitz with Lipschitz constant m. Okay. All right, so let's try and prove this now. So in order to prove this, so this is what we're trying to establish. We're trying to establish this result. If the Hessian is upper and lower bound like this, then the gradient is Lipschitz. Okay. So in order to prove this, we need some results from linear algebra. So again, if these results don't sound familiar to you, Try proving them, proving it yourself. Actually, one of these we already showed in class, but the other two are very straightforward. Okay, you can do it at home. Okay. All right. So the first result says that if you look at X transpose AX, if A is a symmetric matrix, if this is less than lambda max of A times norm of A squared, and norm of X squared, not A squared. Sorry. Okay, so and of course it's lower bounded by lambda min, but it's upper bounded by lambda max times X norm of X squared. Okay, this was another thing we showed this in the second lecture. Another result says that if you look at the eigenvalues of the square of the matrix, A squared. So, so again, this is a symmetric matrix. So this is basically A times A, or you can interpret it as A transpose A, or A transpose. They're all the same thing. So A squared is, you can think of it as just A times A, if you want. So if you look at the ith eigenvalue of A, the matrix A. So I found the eigenvalues of the matrix A, and I ordered them in some manner from 1 through n. And if I square any of those eigenvalues, I actually end up getting an eigenvalue for the square of the matrix. Right? So that's, sorry. Sorry. Okay. All right. So where were we? Yeah. So this is the if I square the ith eigenvalue of A, that becomes an eigenvalue for A squared. And again, this is again very straightforward to show just from the definition of an eigenvalue. Okay, we can try. In fact, it has the same eigenvector as well. You can check that at home. And the other thing is, if a matrix A is upper and lower bounded by mi and minus mi, the minimum eigenvalue of A is lower bounded by minus m, and the maximum eigenvalue of A is upper bounded by m. Right, so all the eigenvalues of A are bounded between plus m and minus m and plus m. Okay, so this is again very easy to establish. Okay, so let's start with those facts and then use them to show this result. So we're trying to show that if the Hessian of F satisfies these conditions, then it's Lipschitz gradient. It's gradient Lipschitz. Okay, so G1, so let's define, let's define G of T first. I haven't done that yet. G of T, let's make it the partial of F at X plus T Y minus X with respect to the ith component. Okay, we'll call that G of T, right? So if I look at G of 1, if I want to write G of 1 in terms of G of 0, I can integrate from 0 to 1 the derivative. Okay, this is the first fundamental. Is it the first or second fundamental theorem of calculus? I keep forgetting. So right, it is a fundamental theorem of calculus, right? So how you relate integrals to the derivatives. So G1 is G0 plus integral 0 to 1 G prime S. And this is a trick that we're going to use quite often. Okay, so what we do is the following. If you look at G1 is actually, by plugging in 1 here, you get Y inside here, right? And if I plug in 0, I get X inside here. So G1 is the same as the partial of F with respect to the ith component evaluated at Y, and this is the same thing evaluated at X, G0. Okay, All right. Now, I'm going to compute the derivative of g of s. So to compute the derivative, I essentially need to again take this is already a partial with respect to xi. To compute the derivative of this, I need to basically, by using the chain rule, I need to take the derivative of this function again with respect to all the components of x, right? And then add them up. Okay, so that's what I'm going to do. So this is a step we have seen before to relate the derivative of these kinds of functions to gradients, right? So this, I'll take the partial again. This is already had a partial with respect to xi, but then I'll take with respect to xj, and from j going from 1 to n, and xt y minus x. And then, since I've taken a partial to the jth component now, what I'm left will be, so basically the jth component y minus x is what I multiply with. That's yj minus xj and ds here. Okay. So now I'm going to take all the components that I've computed here with all the partials with respect to the xi's at y and put them into a vector. That will give me the gradient of f at y. And on the right-hand side, I do the same thing. If I did that, I get the gradient of f at x. And inside the integral, this is already inner product, but what I'll end up getting is the Hessian of f at x plus t, ty minus x times the vector y minus x. So this matrix times the vector will be a column vector, right? And so all these are now column vectors. Any questions?
Shouldn't you write s instead of t inside the integral?
Oh yeah, it should be s. Yeah. Sorry. That's my eraser. Okay. All right. Or maybe I should make my s's all look the same, a little less like that. Okay. All right. So now I'm ready to, I've got the gradient of fy on the left-hand side and the gradient of fx on the right-hand side. In order to prove the Lipschitz condition, I need to take the difference between these two. So I'll take the difference between those two and take the norm of that difference. And so on the right-hand side, I'll end up with the norm of the integral. Okay. All right. Now I'm going to apply the triangle inequality, but the triangle inequality applied to in a continuous manner to the integral. So what the triangle inequality says is that if I add up a bunch of vectors and take the norm, the norm of that sum is less than the sum of the norms. Okay, and that in the limit of that, I can apply the same triangle inequality to the integral. Okay, so you think of a Riemannian sum representing the integral, and then you take before you take the limit, apply the triangle inequality, and then you take the limit, and you'll end up with this integral 0 1, the norm inside the integral. So if I go from norm outside the integral to the norm inside the integral, right, I'm going to get something larger. So I get an inequality going this way. Okay. All right. But now let's actually expand out this norm. So the norm of AX, so matrix, if I look at norm of AX, can be written as basically the square root of X transpose A. A is a symmetric matrix. So A transpose is equal to A. So you get AX like that, right? Or basically this is A squared, right? So what I end up with is the integral from 0 to 1 of the square root of y minus x transpose times the Hessian matrix f x plus s y minus x. This whole matrix squared is like my A squared there, times y minus x ds. This is where I'm going to now exploit the eigenvalue properties, right? So let's call this matrix H, right? Inside, before you take the square. So this is H, the Hessian. So if I look at this result here, it says that if I have any matrix, X transpose AX would be lambda max A times the norm of X squared. So, but now A is like the square of the Hessian matrix. So I'll plug that in there. So this is less than square root of lambda max of H squared times y minus x norm squared. Yes. Okay, all right. But if I look at lambda max of H squared, that is equal to the lambda max of the square of the eigenvalue, maximum eigenvalue of H. But I have to be a little bit careful here. So if I look at lambda max of H squared, this, I have to look at both the largest and smallest eigenvalues of H, because they're going to be squared when I compute the eigenvalue for H squared. So this will be less than the max of lambda max. So suppose lambda max of H is plus 2, and the lambda min of H is minus 4, then lambda min squared is larger, right? So lambda max of H squared will be less than the square of lambda min squared and lambda max squared. But each of these is less than m squared by the condition here, right? By the condition here. Okay, so we conclude that this is less than m times y minus x. You can take it out of the square root now. Sorry, y minus x, not y minus x squared, and then integral 0 to 1 ds. But that's just equal to 1. So we have shown now that basically, if I look at the norm difference between the gradient at y and the gradient at x is less than m times the norm difference at y and x. And so we've shown that the gradient is m Lipschitz. Okay, any questions? All right. All right, so now why is a Lipschitz gradient important? It's important because it'll be useful in proving the following lemma, which is called the descent lemma. Okay, I'll think of it more, or as a lemma that's useful in general when you're looking at gradient descent algorithms and convergence. It's called the descent lemma. Okay, what the descent lemma says is that if I have a function whose derivative, or rather whose gradient is Lipschitz with Lipschitz constant L, then I have this upper bound on this function. So what this is saying is that I can upper bound f of y by something that's quadratic in y. On the right hand side, it's a quadratic in y. So something with a Lipschitz gradient can be upper bounded by a quadratic in y. Okay. Now some of this might look familiar to you already. So if I didn't have the last term, do you remember where this comes from? What is this first two terms? What do they correspond to? Anyone?
Taylor's theorem.
Yes, so it's a first order Taylor approximation, right? For fy in terms of f of x. Okay. Now you remember what happens for a convex function? For a convex function, f of y would have been bigger than the first two terms. Okay, but this is not a convex function we're talking about. We're talking about a function that has a Lipschitz gradient. And in that case, f of y is upper bounded by this Taylor's approximation plus this quadratic. Okay, and we'll see that if the function is both convex and Lipschitz, you're going to get a similar lower bound on the on f, and that can be used to establish. So there are two things you will need to show about these iterative algorithms. The first is to show that they converge, right? And in order to establish convergence, you typically you need to impose a condition like Lipschitz, unless you look at algorithms like that do successive step size reduction, like or backtracking, like Armijo's rule. And the next thing is you need to, if you want to talk about the rate at which you have convergence, you might need a lower bound on the function that's quadratic, and we'll talk about that a little bit later, maybe in the next class. Okay, so this is the descent lemma. I'm going to hold off on the proof until after a short break. But any questions? It'll turn out that we're going to use the same trick, this defining this function g and using the integral, which is why I did that example on the previous page. Okay. All right. Okay. So if there are no questions so far, let's take a short break, and we'll reconvene in 2 minutes. So 11:54 on my clock. All right, so time to get started on proving the descent lemma. Okay, so again, we define this function g of t as f of x plus t times y minus x. So g0 is f of x, and g1 is f of y. Okay, and we have the relationship g1 is g0 plus integral 0 to 1 g prime t dt, and g prime of t we know from a lot of things we've done can be written in terms of the gradient. We've done this in the past several times. Transpose y minus x. Okay, so let's plug that in. So f of y is the same as f of x plus the integral over the gradient. Transpose y minus x dt. Okay, and so now we have, what I'm going to do is the following. I'm going to add and subtract something here, because I have to use the Lipschitz gradient condition. So in order to use that condition, I'm going to add and subtract out here gradient of f at x. Then add back the gradient so as to not change anything. Okay, and of course this is not a function of t. This guy is not a function of t. It can be pulled out of the integral. So I'm going to go ahead and pull it out. And the integral of dt is just 1. So this is fx transpose y minus x. And then I'm left with an inner product inside this integral. This inner product. But to this inner product, I'm going to apply Cauchy-Schwarz. So if I apply Cauchy-Schwarz, I get Cauchy-Schwarz, I should say. I get that this is less than the norm of the difference between these gradients times the norm of y minus x dt. So far so good? Almost there. So what's the difference? Now I'm going to apply my Lipschitz condition. Right? I'm going to look at the difference between these guys. Of the difference of gradients here. So I'll have to relate it to the difference between the arguments is x plus x minus t times y minus x minus x. So the x cancels and I'm just left with t times y minus x. Okay, times L outside. So where did I write the Lipschitz condition? Okay, I haven't really. I just remind you of the Lipschitz condition. So this says that grad fx minus grad fy is less than L times x minus y. Okay, so using that, I get that this is less than L times integral 0 to 1 y minus x times y minus x dt. But that's basically y minus x squared. So as I get L times y minus x norm squared, and then what I'm left inside, oh, sorry, there should have been a t here. Sorry. From when I take the difference of this and this, the t remains, x cancels, the t remains here. And I get the integral of t dt And the integral of t dt from 0 to 1 is equal to half. Okay, and so plugging it all in, I get that f of y is less than the first order Taylor expansion, Taylor approximation for f of y in terms of f of x, plus this quadratic, L over 2 times normal y minus x squared. That's what I have. Okay. All right, so that's the descent lemma. We're going to use this now in looking at convergence with a fixed step size or a constant step size. Any questions? Okay. All right. So again, it's going to be important to choose my alpha to be small. And we saw this in the last class, right? Because if alpha is too large, then you could actually end up increasing the function. So how small is too small? And how large is too large? Okay, this result says that if f has Lipschitz gradients, and I apply the gradient descent algorithm, again, this is just steepest descent here that I'm looking at. By the way, almost all the proofs that I do will be for steepest descent in class. And the book has generalizations of all these proofs for arbitrary decay. Okay, it's just a little more messy, which is why I didn't bother doing that in class. Okay, but you can look at the book if you want to for those results. But just basically what I'm saying is that everything that I show for steepest descent really holds for any descent algorithm, pretty much. Okay. So here's the deal. We assume that f has Lipschitz gradients with constant L. If alpha is sufficiently small, and of course f is lower bounded by some f min for all x, so f is lower bounded, so then we can show that every limit point of x is a stationary point of f. So how do we do this? And we use the same lower bound condition even when we prove that Armyho's rule converges, right? Gradient descent with Armyho's rule converges. Okay, but here we're not doing Armyho. We're fixing the step size. So now we have to be a little more careful. We need the Lipschitz gradient condition. Okay, so let's apply the descent lemma, because that's why we proved it, right? So applying the descent lemma, I can relate f of xk and f of xk plus 1. The descent lemma says that this is less than the first order Taylor expansion here at xk, which would be xk plus 1 minus xk, plus half L xk plus 1 minus xk norm squared. Okay, now I'm going to go back and look at this. Xk plus 1, if I look at xk plus 1 minus xk, that's equal to negative alpha grad fxk for a gradient descent algorithm, right? So I'll plug that in for that difference. So this will give me minus alpha gradient of fs transpose times the gradient of fxk. And then I'll get half alpha L alpha squared gradient of f at xk norm squared. Just plugging in this expression into here and here. Okay, and but this is basically also just the norm of the gradient squared. So I'll have two terms of the norm of gradient squared. I'll club them together. So I get half this alpha times half L alpha. Sorry, let me read that a little more clearly. Half L alpha minus 1 times the gradient of f at xk norm squared. Okay. So now if I look at I'll take this guy, sorry, I'll take this guy to the right-hand side and put it here, fxk minus fxk plus 1, and I'll move this guy to the left-hand side and then change the sign inside here. So I'll get alpha times I was 1 minus half L alpha times the gradient of fxk squared is less than that. I change the sign inside the parentheses. Okay, if I do that, now I'm going to sum. I'm going to take the sum of these quantities. On the left-hand side, from say k equal to 0 to some n. What happens on the right-hand side? The right-hand side also I'll take a sum, but this is what's called a telescopic sum, because if I look at fx0 minus fx1 for the first term, there's a minus fx1 which will cancel out with the fx1 in the second term and so on and so forth. So all the intermediate terms will cancel out, and what's going to be left is basically fx at 0 minus fx at n plus 1. Right? Now I'm going to make use of the fact. So think about this. This is a descent algorithm. So you want it to keep decreasing f, but again, so x. If things are working right, then your xn plus 1 should be moving towards f min, but it's lower bounded by f min. So negative fxn plus 1 is upper bounded by a negative f min. So this is less than fx0 minus f min. Okay, so that's what we've shown here. So the left-hand side is less than fx0 minus f min. And now we'll put a condition on alpha. So finally we arrive at the condition for alpha. So if alpha is between 0 and 2 over L, then that guarantees that this is positive. Right? So alpha 1 minus half L alpha is going to be bigger than 0. Then, since it's strictly positive, then I can divide by that positive number on both sides, and I'll conclude that this is less than f of x0 minus f of f min, sorry, divided by that number, alpha 1 minus half L alpha, which is finite. So if this is finite for all n, it's finite for all n. So basically this means that if I put k equals 0 to infinity here, it's also finite, right? So now I have a sequence which when I sum up from 0 to infinity, I get something finite. The only way that can happen is that if the sequence itself goes to 0. If it doesn't go to 0, then the summation would blow up. Right? So that means that the limit of this gradient function, or the norm of the gradient going to 0, is the same as saying that the gradient goes to 0 in the limit. Okay. All right. But if now that's the sequence grad f xk. That sequence is going to 0. But what about xk itself? Well, xk doesn't necessarily converge. We discussed that before, even when we talked about Armijo's rule. But say x bar is the limit point of xk, of the sequence xk. Okay, that means there is some sequence of indices k, and as k goes to infinity, that if you go along those indices, that you end up with x bar in the limit. That's the definition of a limit point, right? We saw that last class. Again, now we exploit the continuity of the gradient of f, because we assume that f is continuously differentiable, right? So we exploit the continuity of the gradient of f, which is what, again, we did the same thing in the last class in the proof of the convergence of the Army's rule. To conclude that since I'm going on the sequence to x bar, the gradient at x bar must be equal to 0 by the continuity of gradient. So what we have basically shown is that that every limit point of xk is a stationary point of f. Okay. Any questions? All right. So let's actually do some examples here. Okay, so first let's look at a very simple example, a quadratic, right? So and see what gradient descent does with a fixed step size does with a quadratic. So in this case, the gradient of f is just x, and this is Lipschitz with L equal to 1. And now if you look at just applying this gradient descent algorithm, you get minus, the gradient of f is just x, at xk is just x. So this is xk into 1 minus alpha. Now we saw from the previous result that we need 0 less than alpha less than 2 over L, which is in this case 2 for convergence. And let's see what happens. So from previous result, right? Let's see what happens if this is violated. So first, let's take a test case when alpha is equal to 1.5. So alpha is less than 2. In that case, xk plus 1 is xk times 0.5, which means that basically xk, you start off with some x0, sorry, minus 0.5, sorry, minus 0.5, so minus 0.5 to the power k, which is going to 0, which is the minimum of this function as required, right? The only stationary point of this function. And let's see basically what's happening here. Let's say we start at x0 is 2, okay, and then basically x1 will be minus 0.5 times 2, so it'll be minus 1. So it'll be here. Go to this thing here. Sorry, I should have written this as x0 here. And this is x1. And then from there, I'll go here to plus 0.5, which will be x2, and so on. So you'll see that basically you're quickly converging to 0 here, right? You may oscillate a little bit, but you're converging to 0, which is the minimum. Now let's see what happens when the condition is violated. So let's first take the case when alpha is 2.5. Then xk plus 1 is xk times minus 1.5. Okay. Now this is an example where I have a fixed step size. Even though I'm doing gradient descent, I could have my xk blowing up and the function blowing up. So this is an example to illustrate that. Minus 1.5 to the power k. This implies that the absolute value of xk goes to infinity. It blows up. So in this case, basically, if you start here with x0, and then at step 1, you go to 1.5, so you go to minus 3 here. So you end up here. This is x1. So you can see you're going to do that, and then you're going to weigh it out there. So you're going to start blowing up to infinity. Okay. All right. So now let's actually see what happens at the boundary. So maybe things, this was too conservative, but let's see what happens at the boundary. So if alpha equal to 2 at the boundary, 2 over L in this case, then xk plus 1 is the same as xk, xk times minus 1, which means that xk equals x0 times minus 1 to the power k. So here you're basically oscillating between minus x0 and plus x0. Unless x0 happen to be 0, you're not going to converge to the minimum. Okay, so in this case, so if I started here, start anywhere from x0 other than 0. So if I start x0 here, basically I'll go from here and then go to this and keep shuttling back and forth. Start anywhere else, I do that. Except if I start at 0 and then I remain at 0. But any other starting point, I'm not going to converge. Okay, so this condition is actually strict. So if you violate it even a little bit, you can have divergence or oscillation. Okay. Now, what happens if the gradient is not Lipschitz? So this is a problem for which the gradient was Lipschitz, but then you could still have a step size that's too large, and then that could result in poor convergence properties. Okay, but what happens when the gradient condition, Lipschitz condition is violated? So let's do a simple example of that. 3 minutes. I don't know if I can finish it in 3 minutes, but we'll at least get this started. So the gradient here is 4x cubed, or x to the 4th. And we know that x is equal to 0 is the only stationary point for this function. And it's a global minimum. We already know that, right? It's a strictly convex function. And 0 is the global minimum. So let's see what happens to gradient descent when we apply it to this. So we'll get that the gradient is 4x cubed, so you get 4xk cubed. So this is xk times 1 minus 4 alpha xk squared. So that's how the gradient descent would proceed. Xk plus 1 is equal to xk times 1 minus 4 alpha xk squared. Okay, so let's look at some cases here. Okay, so by the fact that this recursion holds at every step, if it so happens that x1 is bigger than x0 in magnitude, then the same should hold for all k because it's a recursion, right? So then basically xk plus 1 should have a larger magnitude than xk for all k. And so basically, if you start at any point, you're going to have a larger magnitude from there. So there's no way it's going to go to 0. So in this case, xk stays bounded. Even if you start at 0, you're going to be larger, right? So it's bounded away from 0. What happens if x1 were equal to x0 in magnitude? Then xk plus 1 equal to xk, right? Which is equal to x0 for all k. And so in this case, again, the sequence will stays bounded away from 0, except when? What condition holds? Except if I started at 0. If I start at 0, I remain at 0, but that's the only case. Okay, so finally, the only way we can have convergence, so even if the Lipschitz condition doesn't hold, you could possibly have convergence to 0, but then maybe it'll depend on the starting point now. Okay, so if x1 is less than x0 in magnitude, then xk plus 1 is less than xk in magnitude for all k. And so what does that imply? When will x1 be less than x0 in magnitude? So that says that x0 times 1 minus 4 alpha x0 squared is less than x0 in magnitude. So this will cancel. So that means that what I have in here, 1 minus 4 alpha x0 squared should be less than 1 and bigger than minus 1. Now, if I look at the condition that it's less than 1, this will cancel, and that all that tells me that is that alpha should be positive. If I look at this other condition, that tells me that alpha should be less than 2 over, sorry, x0, I meant x0, alpha is already positive. So this condition will give me that x0 should be bigger than 0. And the other condition will tell me that x0 should be less than 1 over 2 alpha. So this is basically 0 less than x0 squared, which of course will hold if x0 is non-zero, and then less than 1 over 2 alpha, which basically means that x0 itself is bigger than 0 in magnitude and less than 1 over square root of 2 alpha. So if the magnitude of x0 is less than 1 over square root of 2 alpha, so if I started at a point with that condition, then I'm at least decreasing. It'll converge to something. So xk converges in this case, right? But does it converge to 0? You expect it to converge to 0, right? So, but you need to prove it. So the claim here says that if this condition is satisfied, then xk does converge to 0. Okay, and I'm kind of out of time, so you can look up it's a very straightforward proof to show that this condition is satisfied, that it's xk converges to 0. So you can look it up in the post-class notes, and we'll talk about it again maybe in the next class anyway. So any questions? So the bottom line is that if the gradient is Lipschitz, okay, and if my step size is chosen carefully, I can guarantee convergence. If not, if the step size is chosen too large, then I may not have convergence, and I could have divergence, it could blow up, or I could have oscillation. If the Lipschitz conditions is not satisfied, then for a general starting point, I'm not guaranteed convergence anymore. But if I choose my starting point carefully, I could still have convergence. Right? That's what this is saying. And that's the example we just saw. But in general, I cannot, for any arbitrary starting point, I cannot guarantee convergence without the Lipschitz condition. Okay? All right. So there are no other questions. Any questions? Okay, so I'll see you guys on Tuesday.